Hello, welcome back to our series of videos on the Claisen condensation. You may notice I have a new assistant with me tonight. Professor Chicky Chick, I should say, was kind of making me feel dumb in the last video, so just need a little break from her. So I brought in Monkey to help me out tonight, or with this video. So what we're going to look at here is something known as the Diekmann condensation, and this is a Claisen cyclization, okay? And I'm going to give you an example here and then kind of walk you through what's going on. So what I have here is diethyl pimolate, and that is a 7 carbon. Well, it's got more than 7 carbons. 7 plus 4. Okay, all right. It has 11 carbons, but it's a 1,7 diester. All right, and if we react that with sodium methoxide, notice I've matched my base to the type of ester. If I have ethyl here, I want ethyl here. Okay, and then we're going to have a second step with H3O plus, and I make this ring. Okay, and this ring, you might notice, this is the alpha carbon, this is the beta carbon. It's a beta ketoester, okay, which is what we make with Claisen condensations with 2 esters involved. Okay, so let's go over how do we get to this 6-membered ring. And I may or may not go through the full mechanism of this. But I'm going to give you at least, if you want the full story of the mechanism of a Claisen condensation, you need to watch the previous video. Okay. But what's going to happen here is our base, methoxide, is going to come in, and we're going to do a proton transfer. Okay, PT. We're going to form an enolate. Then I'm going to proceed to try to not drop off a bunch of carbons. 2, 3, 4, 5, 6, 7. All right. You may think I've lost my marbles, but really I've just lost a couple carbons. Okay. All right. So there we go. There's my enolate. Enolates are nucleophiles. They like to attack electrophiles. Here's an electrophilic carbon, a carbonyl carbon. Okay, so I'm going to do a nucleophilic addition to all sorts of lone pairs here. Nucleophilic addition. Okay. And here's where the numbers become very important, okay? I'm making a bond between carbon 2 and carbon 7, okay? So whatever I draw, I need to make sure carbon 1's connected to carbon 2, carbon 3's nestled in between carbons 2 and 4, okay? If you find numbers in places they shouldn't be, you need to rethink your connectivity here. Okay, so here's carbon 1, there's carbon 2, all right, and I'm going to walk around the ring here, 3, 4, 5, 5's between 4 and 6, 6 is bonded to 7, and we made a carbon-carbon bond between 2 and 7, that's my new CC bond, and okay, there's O minus, OET, my soon-to-be leaving group. Okay. Now we've done the hard part. All we have to do is get rid of that ethoxide. And that's going to be a nucleophile elimination. All right, and that gets me here And there's my product. Okay, 1, 2, 3, 4, 5, 6, 7. Okay, now if you remember from the previous video, okay, this hydrogen on carbon 2 has a pKa of about 11, so it's very acidic. So another molecule of ethoxide is going to come in and pull this off, so we're going to have another step with H3O plus that puts it back on. Okay. And by the way, that's having to do those next two steps, or that they happen, is the reason why this Claisen condensations are considered base promoted rather than base catalyzed, because you have to use a full equivalent of your base. Okay. Do I have time for one more example? Maybe. All right, this one we'll try to do in a little less detail. Okay. How am I going to do this? Okay, so this is always... Oh, I shouldn't do this stuff on the fly. This will get me in trouble. All right. Well, it's not exactly on the fly. I did read a little bit before... Okay, 1, 2, 3, 4, 5. Ooh. Okay. Here's another diester. It's really not that different from the other one. 1, 2, 3, 4, 5, 6. A little bit shorter, and I just to keep things interesting, I threw a 5-membered ring in the backbone here, and and that light I threw it in on carbon 4. Sorry. Okay, maybe I should turn that back off. Oh, not that one. All right. And so what's this gonna form? Okay. We've got a couple. Actually, we only have have some symmetry in this molecule. I just drew it such that it doesn't look like we have symmetry, but we actually have a line of symmetry going down there. So it doesn't matter if I form the enolate on carbon 5 or on carbon 2. I should get the same product. But I'm going to form it off of carbon 2. Okay, so we're going to make an enolate at carbon 2. That's going to attack carbon 6. We're going to do a nucleophile addition. We're going to eliminate ethoxide. Okay, and then we're going to have a bond between 2 and 6. So my product... So my ring that I'm going to make is going to be made with carbons 2, 3, 4, 5, and 6. Wow. Okay, carbon, so there's, I'll get my numbers up there, 2, 3, 4, 5, 6. The new bonds between 2 and 6. And carbon 6 has a carbonyl on it. Carbon 2, coming off of that is my ethyl ester. Okay, so that's my product. Okay, and can you see that? I don't know. And 2 is the alpha carbon, 6 is the beta carbon. We've got a beta keto ester. All right, and that's gonna conclude my video on the Dieckmann condensation or Claisen cyclization. In our next video, we're going to look at some crossed Claisen reactions. So thanks for watching.